Finally, let's look at the quick analysis of this algorithm. So when we look at initialization, the only thing that takes time here is this sorting operation that takes n log n time, and then we populate the priority queue with this. So that takes initialization takes n log n time. Then we have a while loop. Okay, the while loop is slightly complicated because we don't know how many events we're gonna run, but we could use this parameter k to come up with a bound, because we know that there are two n top and bottom event points, and then there are k intersection event points. So that therefore the size of this priority queue is at most O of n plus k, and therefore this while loop runs n plus k time. What do we do inside each loop? We first get the next event point, and then we might insert it into our binary search tree. We might delete it from the binary search tree, and we also need to do some kind of search in a binary search tree to find the next and the previous things. And we also need to do some additional insertion of intersection points into this binary search tree. Okay. Each one of these operations take log n time in the worst case, if you're using a balanced binary search tree implementation. So therefore, we have a log n time per event. So every iteration of the while loop runs in log n time. Since we have n plus k iterations, so therefore the total time is n plus k times log n, or n log n plus k log n. This n log n time is obviously optimal. This part is, technically not optimal, because with more complicated data structures or solution, you can remove this log n part. But it is close to optimal because we need to output all the intersection points. So we need to output k things. So the running time cannot be smaller than n log n plus k. But we can, so we are almost there. We have only this extra log n factor, so this is not so bad. So the only real big problem with this solution is that in the worst case, this might consume n plus k space, which is actually a problem, because even though it might seem at the beginning not intuitive, but running time is actually a suboptimal running time is more tolerable than a suboptimal space. In other words, a space is generally much more expensive than running time, because typically we can assume that you have fast CPUs, you have multi-cores, and etc. So there are always ways to shave off factors from your running time. But a space is not so good to have extra, or to use extra. In particular, because if you use more space, then your caching also degrades, etc., etc. So ultimately, having optimal space is actually very crucial. And in fact, in this algorithm, there is a way to improve the space to linear. And again, I'm going to talk about that in the exercise classes. But that concludes the analysis of this data structure, or this algorithm. N plus k space and n plus k times log n running time.